First of all, I would like to thank the organizers for this interesting and thought-stimulating meeting in such a beautiful location. So this is not exactly the audience that I normally talk to. I usually work on the phenomenology of quantum gravity. So before I begin, I would like to say a few words about what brings me here. The problem of quantizing gravity has been known for about 80 years now. And, well, to be precise, the problem is not actually to quantize gravity. You can quantize gravity all right in the perturbative limit. The problem is that the theory you get this way is not renormalizable, and so it does not make sense as a fundamental theory. So what you can do then is that you look for other more suitable degrees of freedom that you quantize, and there are several approaches to this. Might be strings, loops, partially ordered sets, little triangles, what have you. But the bottom line is we do not yet have a theory of quantum gravity. And I've become convinced that the problem is not that we have not found the right degrees of freedom to quantize, or that there's something about gravity that we don't understand, but there's something about quantization that we don't understand, so that the problem is on the other side. And that's basically what brings me here, because I believe that one of you guys has the missing piece of the puzzle that will solve my problem. So once I started interacting with people who work on the foundations of quantum mechanics, I felt like I had to get an opinion. And I came down fashionably on what turns out to be pretty much the most unpopular approach to the foundation of quantum mechanics, which is superdeterminism. So I do not believe in free will. It is somewhat beyond me how anybody who believes in reductionism can believe in free will, but that would be a different talk. So, and I'm trying to be consequential about it, and so superdeterminism is the natural consequence. It's been said before, but what I mean with superdeterminism is that it is not possible to choose the detector settings independent of the prepared state. These theories are also known not so nicely as conspiracy theories, because it seems to imply that the experimenter cannot turn the damn knob. But I think this is a fairly misleading expression. What it really means is that you cannot prepare the state independently of what the detector does. So yes, non-local correlations are necessary. These superdeterministic hidden variable theories have non-locality, but I think it's a soft version of non-locality, one that I'm fairly comfortable with. You do not necessarily have some kind of spooky action at a distance or superluminal propagation. And so you have probably all seen this figure before, which is from Bell's book. So in a superdeterministic, I should probably first say, so this is kind of a sketch of a space-time diagram, and these are light cones. So in the superdeterministic theory, what happens in the space-time region 1 is not independent of what happens in the space-time region 2, but it is perfectly fine that it be entirely determined with what went on in the space-time region 3. Just that what was in space-time region 3 might not have been independent of what went on in 4 to begin with. So these theories are non-local according to the first part of this definition, if you had a chance to read it, but not according to the second part. So yes, they are non-local, these theories. But it's not necessarily, you do not necessarily need to have any superluminal propagation of information. Okay, so this is the point where I give you a convincing explanation for why superdeterminism is the most natural and elegant solution of all our problems. But the truth is, I just like it, and I believe that it's the right description. I had a teacher who liked to say, belief belongs into the church. So as a scientist, I should not think too much about what we believe or what you believe, but whether it's possible to test it. So the thing with superdeterminism is it's possible, and it hasn't been ruled out since Bell's theorem cannot be used. The detector settings are independent of the prepared state is one of the assumptions that goes into the theorem, and any theorem is only as good as the assumptions that go into it. So before I go on, I have to say that logically you can never rule out superdeterminism, basically for the same reason that you can never rule out that Elvis Presley was murdered by some evil alien that popped up a wormhole with some technology that we have never heard of and sent over some poison to kill the poor man, something that we cannot detect. But you can rule out certain specific theories, like you can rule out that he didn't break his neck, that he was not eaten by a dog, and so on and so forth. The only thing that we can do is to rule out some specific model for superdeterminism, though in that I will try to be as model independent as possible in the same sense that Bell's theorem is pretty much model independent. So what kind of superdeterminism will I be talking about? I'll assume that the hidden variables come from the environment, so that's everything that belongs to the setup of the experiment that you're doing, including the detector. I'll assume that the degrees of freedom that are beyond the experiment scale, so the experiment works at a certain energy scale, something like this, and there are degrees of freedom far beyond that cannot be resolved, and I will assume that these do not matter. So I'm not worried about Planck scale noise and so on and so forth. I will also assume that the Born rule is fulfilled, so basically, well, we know that quantum mechanics is right, so it has to come out in the end. And I'll not make any assumptions about collapse and so on. And so that's basically it. So how do we test superdeterminism? The main difference between superdeterminism and standard quantum mechanics is that the same initial state will always lead to the same outcome in the superdeterministic case, whereas in standard quantum mechanics, you have this probabilistic distribution. So there's no indeterminism. But the problem is that the same state now means it's the same state, including all the hidden variables. But the hidden variables are hidden, so you cannot measure them. How do you know that you actually have the same? That's exactly what reproduces the apparently probabilistic distribution of standard quantum mechanics after all. So if you just prepare one state after the other and you measure it, you have the problem that you don't know what your hidden variables were. And I think that it's possible to avoid this problem by repeating measurements on the same state. And you have to repeat them quickly enough so you can be sure that the hidden variables didn't change in between. In particular, it seems suitable to use non-commuting variables. And measure these repeatedly. So this is very similar to the experimental setup that we heard of before the lunch break. So you have something like a Stern-Gerlach-like experiment where you measure the spin in two different directions. So these are non-commuting variables. You measure them alternatingly. One after the other. So whenever you measure the second one, you screw up the measurement of the first one. And you repeat this. So if you do this, then the time between the measurements needs to be short so that the environmental variables don't change. That depends on the details of the experimental setup. If they do, then you get the indeterminism back because you add your hidden variables to the system and then you get your randomness. Okay, so here's a sketch of how I'm envisioning this. You have some beam that comes in, so that might be an electron where you measure spins in two different directions, or it might be photons where you measure polarization, so it doesn't really matter. So this is something like a one-way mirror or a similar experimental device that fulfills the same purpose. And once this particle is in, it keeps bouncing back and forth between the sites, and the red and the blue bar indicates the measurements of the two non-commuting variables, so the spin up and the spin left or right, as I've written here. And so now you choose one particular combination with which the particle passes through. The example that I've chosen would be up and left, and if the particle does not have this property, then it leaves the system. So what you measure is the time that it takes before the particle gets thrown out of the system. So in normal standard quantum mechanics, what would happen is that whenever the particles get measured, there's a 50% chance that it gets thrown out. The same happens at the next measurement. It goes back. Now you've screwed up the first measurement, and again, there's a 50% chance that the particle gets thrown out. And this probability that the particle stays inside the system goes to zero fairly quickly. Now, in the superdeterministic case, the second measurement does not screw up the first one. So the particle gets either thrown out or it doesn't. And same is the case at this measurement. But if it stays in after the first measurement, in principle, it would stay in forever. It would just keep on bouncing, 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 bouncing. Up to the point, though, where the noise from the environment becomes noticeable and you feed in your hidden variables into the system, and then this correlation goes away. So basically what you have to measure here is the correlation time between the subsequent measurements. And that's what this time until the particle comes out basically gets at. Okay, so having said that, it's pretty clear what requirements this experiment needs to have. It should be as noise-free as possible, meaning it should be small, cool, and well-isolated. You have to measure fairly quickly. So these measurements need to be briefly after each other. They shouldn't be too briefly after each other so that you can still measure them. You measure the correlation time, so basically that's the expectation value for whatever observable it is, for example, the spin, at the time where the particle enters the system, and then every 2 steps later. So these observables are the same, and then there's a normalization. There is an ansatz for the decay of this correlation time, which is exponentially. And in my paper, I had a good reason why I made this ansatz, but it's been 2 years and I forgot it. But it's a very standard ansatz for the decay of the correlation time. So the question is then, how do you estimate the decay time tau that goes in here? And so I put in some numbers. So consider you have a detector, let's say photodetector, works by exciting some electron into the conducting band with the energy gap being delta E. The thing is at a temperature of T. So then you have a Boltzmann factor for the population of these energy levels. There are n particles into the system, and the thing scales with the electron-hole recombination time, which I looked up somewhere. And so for typical semiconductors that you would use in such a setting, it might be something like a nanosecond. So now you want the whole thing to be small. So I'm thinking of something of the size of millimeter, fraction of a millimeter down to a micrometer, and I'm being told that might be possible. The quantum informations people can do that just fine. So that gives you something like 10 to the 15 atoms. And now you can just put in the numbers at something that is moderately cooled with a fairly large band gap. You get a correlation time which is about 10 to the minus seconds. And that doesn't seem hopeless to me. I think one could actually measure this. So, yeah, so here's a historical footnote. I talked about this to Chris Fuchs at some point, and he amazingly, in the moment I told him about it, was like, do you know this footnote in the paper from 1970 by Wigner? And I was like, I don't even know the paper. I have no idea what you're talking about. And he sends me the reference. And it turns out that in that footnote, Wigner recalls how von Neumann used to discuss exactly that type of experiment with the repeated measurement of the non-commuting variables. So it's too long to read it, but just trust me, it's basically the same thing. It doesn't end there. There's a longer story in which Schrödinger disagreed with von Neumann that this way you could not test the superdeterministic hidden variables, and then there were other people who had something to say about this. The bottom line of this discussion is basically that it depends on exactly what determines the superdeterministic hidden variables. As I already said earlier, you can never rule out that there are unknown unknowns, that there is some evil alien that creates some wormhole. Okay, so this might come as a shock to some of you, but this is actually my last slide. To briefly summarize what I told you, superdeterministic hidden variable theories cannot be tested using Bell's theorem. Then that's the question, what do we do? I'm saying, well, we use repeated measurements of non-commuting observables. If the hidden variables exist, these measurements' outcomes should be correlated, provided that you measure in a small system and in a cool system where you do not have a lot of noise, and you can make an accurate time measurement. So in the end, you might not be able to rule out that Elvis Presley was moderate, but you might be able to rule out that he was run over by a bus. So thank you for your attention.
So thank you very much. Questions? Yes? Yeah, you.
That's very interesting. Have you thought about the implications if an experiment like this actually did find deviations? Because this is presumably, this is not what quantum mechanics predicts. So given that, I mean, would it, for example, enable superluminal communication or something like that? Have you thought about what, where it could lead?
I've thought about it a little bit, but it's hard to say since, as I said, I try to make this as model independent as possible, so I don't actually have a model. I suspect that it's not possible because, at least the way that I think about the superdeterministic hidden variables, there is no superluminal exchange of information going on.
No, okay. I guess it's just that there are results that say that, you know, generically any deviation from quantum behavior, you know, which is compatible with other things that we observe in quantum mechanics leads to, you know, strange things like superluminal communication. That's why.
Yeah.
Okay, Helmut, you had a question.
Okay, I would have a question. Let's say, is that connected to the so-called Zeno effect? Measurement, because there, when you do very fast, repetitive measurements, then the system has no losses or does not decay at all. So that is, in principle, a quantum effect. Does that also appear here? You know, there's the Zeno effect between
yes,
energy levels.
I'm digging in my brain what I've read about it at some point, but I can't. I really don't know enough about it, but I looked at this at some point, and I think it's not very closely related. Because I think that the trick in this situation is that you kind of keep the state in the same state.
Yeah. Okay.
So another question over here. Here. Yeah.
Now, standard quantum field theory, of course, does have a model, which is the standard model. And one of your primary concerns would be how come that the standard model works so well if it already would deviate at this level? The length and time scale of the standard model is 10 to the minus 15 centimeters or something like that. And that's, of course, much, much shorter than what you talk about. Aren't you afraid, actually, that the time scale where this really happens could be as small as a Planck scale, which would be totally out of reach of experiment?
Well, you don't normally make measurements at this scale.
Okay, but you would think that at even shorter scales, you would then have to conclude the same thing. Although you can't do measurements.
It depends on the energy that you're resolving. That's what I said earlier. So if you use a higher energy, then you get sensitive to more degrees of freedom. So then you have more noise in the system.
Okay, but anyway, I would think it is a problem to ensure that the good things of the standard model stay untouched. I mean, you might address the bad features, which is, I agree with the basic idea, but I'm worried about the scale.
Yeah, you can start.
Can you specify a bit more exactly what you mean by degrees of freedom beyond the scale of the experiment decoupled?
Oh, well, basically, I mean...
Space or...
Huh?
Space, for example, in terms of space.
Yeah,
We
space.
talk about energies, but if I do something somewhere else in the universe, is that decoupled or is that...
Yeah, it's decoupled. Basically, so everything that you can take away and it doesn't change anything about the experiment that you're doing, you know, the experimental setup, the detector.
How about, say, the Tenerife experiment where they had random number generators somewhere outside the light cone of the source? Would that not already rule out your type of superdeterminism?
Well, you're talking about the experiment where they sent the photons between the different islands. Well, so it's a huge system.
Settings were chosen outside the light cone.
Yes, but you also have the detectors themselves on both sides, and these are huge things. So there are lots of degrees of freedom that reproduce standard quantum mechanics.
But they wouldn't produce correlations.
No, in this case, you reproduce the.
You don't care about the detector because the setting that you produce somewhere else is what you use to evaluate the current correlation. So no matter what you do there, it will not help. It will not help.
Sorry, I don't know what you mean. So what I'm saying is the larger the system is that you use for your experiment, the more reliably will you reproduce standard quantum mechanics. And they have, of course, confirmed standard quantum mechanics. So I don't see the problem.
Okay, so we can take one more question. There was one more question in the back.
I'm sorry, I have very basic question. I missed actually in which way this is a test of a superdeterministic theory, because at no place where the choice of the measurement device were involved in the setup. I'm sorry, maybe I missed something.
I make it through the correlation between the subsequent measurements. So you could say, okay, maybe it's not superdeterministic hidden variables, but just hidden variables. But then we know that if the hidden variables are local, then you can use Bell's theorem.
They might be non-local, but still with the freedom of choice. So I'm confused what it really tests. I didn't get fully.
Yeah, you're right. So I'll have to be more careful on this point.